Welcome to section 5.3. What we're talking about here is solving trig equations. So solving trig equations slightly different than solving an algebraic equation. So we are still going to use algebra, but we have to deal with how to solve when we've got sine, cosine, cosecant, and things like that. With trig equations, we will first solve for the trig portion of the equation by using inverse operations. Oops, sorry, I'm not writing with a pen right now. So let's try that again with inverse operations. So we're talking about inverse operations. We're talking about, addition, subtraction, multiplication, division, squaring, and square rooting. Then we use our knowledge of the unit circle. So we have to be referring back to 4.2, all that unit circle stuff, to help us solve for the trig portion of the equation, not the inverse functions. So we use inverse operations, but we do not use inverse functions. So we're not going to use stuff like inverse sine or arc cosine, which is sort of how we dealt with some of those problems in chapter 4. The difference is in chapter 4, what we were looking for was a specific angle. And in chapter 5, what we're going to be talking about is how do we come up with what are called general solutions, meaning a solution regardless of domain. So, for example, if we consider the equation 2 cosine x minus 1 equals 0, we would solve by first adding 1. So, I'm over here out to the side, I'll do the solving. 2 cosine x minus 1 equals 0. We add 1. So I get 2 cosine x equals 1. Then divide by 2. So if I divide this by 2, I get cosine x is equal to 1/2. From here, we are not going to use the inverse cosine to solve. And the reason for that is that arc cosine would only give one answer. So arc cosine only gives one answer. And when I talk about cosine x being equal to 1/2, there's not exactly just one answer to this. In fact, what we know is that there are actually an infinite number of answers. Or infinite number, sorry, of answers to this problem. So what we want to talk about is how do we write the answers to this? Now, let's take a step back. What if you're like, whoa. How do you know that there's an infinite number of answers? Well, remember that the way that cosine looks is like this, but then it just keeps repeating. So if I said, like let's say right here, cosine is equal to 1/2. This is 1, so here's 1/2. Well, it's also 1/2 here, and here, and here, and here. And it just continues going and going and going. So what we want to do is write an answer that represents all of those points. So I'm going to go back to that problem that we had, cosine x equals 1/2. What I do is I then go to the unit circle and I think about, okay, well, where is cosine x positive 1/2? Cosine is my x values, and x is 1/2 here and here. So this would be pi thirds and 5 pi thirds. So we would say x equals pi thirds and x equals 5 pi thirds. But there's an infinite number of answers. So it's not like I just get pi thirds and just get 5 pi thirds, because it's going to keep repeating. Here was pi thirds, here was 5 pi thirds. Here was some other thing and some other thing and some other thing, and so on and so forth. And that's where we talk about the period of the function. So we talked about period when we talked about the graphing of these functions. The period of this function, since this is cosine x, the period here, remember, is 2 pi over absolute value b. So the period is 2 pi. That means that I can write this as pi thirds plus 2n pi and 5 pi thirds plus 2n pi, where n just represents that you can take any multiple of 2 pi. So, if I took pi thirds and added 2 pi, that would get me right here. And if I added another 2 pi, that would get me right here. And so on and so forth. It would keep giving me 2 pi later. So this would be our general solution to the equation cosine x equals 1/2. Notice this is unrestricted. It's not on a specific domain. So when we allow for an infinite number of solutions, we refer to the solution as the general solution. But occasionally, we are not looking for the general solution. For instance, if I told you to solve for x, but then gave you the domain restriction of 0 to 2 pi, we're going to subtract the square root 2, so we get 2 cosine x equals negative square root 2, and divide by 2. So cosine x equals negative square root 2 over 2. In this case, we can go back to our unit circle and say, okay, here's where cosine is negative root 2 over 2. Now this is two different angles. It's x equals 3 pi fourths and x equals 5 pi fourths. What we can start with is by writing a general solution. If we wrote a general solution, we would say, okay, looking at this, the period is 2 pi. So this would be plus 2n pi and plus 2n pi. Again, where n just represents the fact that you can take any revolution of 2 pi. So if n was negative 3, that just means I'm subtracting, but I'm going to get something coterminal. Now, this is the general solution. If I am asking for just in the interval 0 to 2 pi, well, I would have 3 pi fourths, 5 pi fourths, and then you need to ask yourself, okay, if I added this period, if I added 2 pi to 3 pi fourths, I would no longer be between 0 and 2 pi, because I'm adding 2 pi plus some number. And same thing here. 5 pi fourths plus 2n pi, I would no longer be within this domain. So this would be the only two answers here. But that's not always the case. If this was just n pi, theoretically, I am able to add pi to this and still be within the domain. And you'll see problems like that. I'm just sort of setting the tone for it. All right, so that's all I'm actually going to go through in this notes video. Everything else is just examples of solving some of those. Definitely pay attention. Go look at them. It's a not that bad topic once you get it down. But if you don't get it down, general solutions can be quite nasty. You do need to know the unit circle. So if you need to go back, study that, get that down and get down where all those x and y coordinates are. Otherwise, jot down if you have any questions and make sure that you ask them in class.